Now let's consider some examples. To start with, we have the integral from 1 to infinity of 1 over x to the fourth. We have defined this as the limit as b approaches infinity, the integral from 1 to b of 1 over x to the fourth, which I'll write as x to the minus 4. And the way we'll solve this is by first evaluating this integral, giving us something dependent on b, and then taking the limit. The antiderivative here is x to the minus 3 over minus 3, and we're evaluating this from 1 to b. And so this yields the limit now of minus 1/3 times b to the minus 3 minus 1. And now I'm at the stage where I can take the limit. If I send b to infinity, because this is the same thing as 1 over b cubed, this is going to approach 0, and we'll get 1/3. So we can say that this integral converges, and that it converges to the value 1/3. Another example, if we integrate from minus infinity to 5, the function e to the minus x, we can define that as the integral, or excuse me, the limit as a approaches minus infinity, the integral from a to 5 of e to the minus x. So we're taking the limit here and the last step, and our antiderivative is minus e to the minus x, where we're evaluating x from a to 5. So we need to find the limit as a approaches minus infinity of e to the minus 5 minus e to the minus a. And notice here that we have the minus a, and our a values are also negative. So those negatives will cancel, and this is going to essentially look like e to an exponent that's approaching infinity. So this term is going to infinity. And so in this example, what we'll say is that the integral diverges. We don't approach a finite limit. Unlike with the case of convergence, we don't ever say or need to say that it diverges to infinity or to minus infinity. It suffices simply to say that it diverges. If we were to look at the integral from minus infinity to positive infinity of 1 over 1 plus x squared, here we see that both limits of integration are infinite. And in our definition, we said that we could split this up into two pieces. So I could have the limit as a approaches minus infinity, the integral from a to any value, I'm just choosing 0, of the integrand, plus the limit as b approaches positive infinity of the integral from that same number 0 that I picked to be the same thing. The antiderivative here is the arctangent. So we are finding the limit as a approaches minus infinity of the arctangent of 0 minus the arctangent of a. And then we're adding to that the limit as b approaches positive infinity, arctangent of b minus arctangent of 0. So to think of these limits here, I'm going to kind of leave a little space to put my answer. But thinking about my limits, if I'm looking for the value of arctangent of b, and I'm saying that b approaches infinity, thinking of the relationship between tangent and arctangent, they're inverse functions. So if we say that y is the arctangent of x, that implies that tangent of y is equal to x. So what we're trying to figure out is what the input value of tangent would be approaching as the output value is approaching plus or minus infinity. So if you envision the graph of tangent, remember that it has asymptotes at plus or minus pi over 2. So for this part here, as I look at the arctangent of b as b goes to infinity, what I want to look at on the graph of tangent is as the y value approaches infinity, what is the x value approaching? And what we see there is it's positive pi over 2. I can do the same thing to get this limit over here, and we see that as the y value is approaching minus infinity, the x value on the tangent graph is approaching minus pi over 2. And alternatively, we could have gotten there by thinking of tangent as sine of y over cosine of y. The denominator is 0 at plus or minus pi over 2, effectively giving us those plus or minus infinity. And to distinguish between the positive and the negative, we think about when the numerator is positive or negative. Either way, we get our limiting values here. And then the last thing to consider is the arctangent of 0 is 0. So we're left with pi over 2 plus pi over 2. We get that this converges, and it converges to pi. Notice that my choice of 0 only came in these stages here. And we see that if the integral converges, then those are effectively going to cancel off. So in this example, it might look like that didn't really serve any purpose, but it really does. And in particular, it helps us to break this into two pieces, because in our definition, we said that we need both of the integrals that we introduced to converge in order for the original one to converge. So as a cautionary tale here, I want to point out a common misconception. So maybe I'll put it here. It's not always true that the integral, or let me write it this way. So the common thing that I'll see is that the limit as t approaches infinity of the integral from minus t to t. So that is what I see people wanting to do, to skip steps. It's not always true that that's equal to how we defined the integral from minus infinity to infinity, that you break it up from a to c and let a go to minus infinity, and add to that the integral from c to b and let b go to positive infinity. So this is important. We don't want to do what's on the left. And to see an example of what the distinction is there, if we take the integral from minus infinity to infinity of simply x, again, I can break that up into its requisite pieces. Consider the integral from minus infinity to, say, 0, and 0 to positive infinity. And our antiderivative here is x squared over 2. And we would evaluate this from a to 0, and then also from 0 to b. But if we do that, we're going to end up with here basically 0 minus a squared over 2 plus the limit as b goes to infinity of b squared over 2 minus 0. Now, in this first limit, we're going to get minus infinity. And in the second one, we're going to get positive infinity. But we said as soon as one of those pieces doesn't approach a finite number, then the original integral diverges. And that's our conclusion here. The wrong way to approach it was what I said I commonly see students wanting to do, is to simply kind of avoid that middle step and think about expressing this as the integral from minus t to t of x. Notice what happens here, because we still hold the limit for the end there. We're going to get antiderivative x squared over 2. And if we plug in the bounds, we get t squared over 2 minus the quantity negative t squared over 2. But that's the limit of 0, because those cancel, and that gives us 0. So if we did it this way, we would get a very drastically different conclusion, that the limit is 0 so that it converges. And what this really comes down to is the fact that we can't say that infinity minus infinity is 0 in the way that we can say 5 minus 5 is 0. So if I think of the graph here of y equals x, we're getting infinite area on either side. One side it's positive and one it's negative. But as soon as that's infinite, we talked about that being an indeterminate form, that it's not an obvious condition about how we would treat those. And we want to start to consider infinite areas in any form as an integral that diverges. So be careful, don't fall into that trap. And then I want to look at one last example, and I want to say for which values of p does the integral from 1 to p of 1 over x to the p converge. So this is going to be a more broad example, and it's also something we'll be able to refer to when we talk about series. So to start with, I want to think about my antiderivative here. So we're going to say that the integral from 1 to infinity of what is effectively x to the minus p, that is a limit as b approaches infinity. And the antiderivative I can express as x to the minus p plus 1 over minus p plus 1. But importantly, I can only do that if I'm assuming p is not 1. Not only would that make the denominator 0, but also 1 over x has a very different structure for its antiderivative. So I'm going to have to look at that separately. We're evaluating this from 1 to b. So we're getting here, again, we're taking the limit. I have the constant 1 over minus p plus 1. That's constant for this limit. I have b to the minus p plus 1. And then minus, when I plug in 1 and raise it to that finite value, minus p plus 1, that's 1. So what we're interested in is this part here is the only thing that changes with b. And we want that to be finite so that this limit exists and is finite in order for convergence. So b, the base, is going to infinity. So notice that what we really need is we need to ensure that our exponent is negative so that we know that that does not blow up to infinity. So we need this to be negative. And if you add p to both sides, that means we need p greater than 1. So we're finding now that if p is strictly greater than 1, this integral converges. And consequently, if it is strictly less than 1, it diverges. In that case, you'd have b raised to a positive exponent, which would be infinity. And we said that that's divergence. The only other thing we have to consider is the case p exactly equal to 1. And like I said, in that case, our antiderivative is different. The antiderivative is now the natural log of the absolute value of x. And so we're simply just taking the limit as b approaches infinity of log of absolute value of b minus log of 1, which is 0. But the natural log of b, as I let b approach infinity, that too is going to approach infinity. So in the case where p is equal to 1, we get that it diverges. So putting that all together, we get divergence for strictly less than 1, for equals to 1. And so this integral converges when p is strictly larger than 1. So that's something that is going to be particularly useful later when we talk about series and we talk about p series in particular.